This lesson today, I want to go over number 4 really fast from the worksheet. So, you got the peanut, strip, and the rod. Okay. And to find the electric force, you just take it in pairs. So you cover up, you ignore the rod, and you find electrical force between those two. Okay. And the peanut is being repelled by the strip, and the strip is being repelled by the peanut. Everybody see the color coordination there? Okay. And then you cover up the strip, you ignore the strip, and you find the electrical force between the peanut and the rod. So they're oppositely charged, so there's attraction. And there's attraction here. Good with that? Okay. And then between the rod and the strip, there's attraction. And attraction. Good with that? Now, to find the net force, here's what a lot of people, most people can handle getting the numbers. But how do you combine, how do you find the net force? So here, this is being forced to the left, this is being forced to the right. So you're subtracting those two because they're going in opposite directions. You do not care about like, oh, is it attraction or is it repulsion? You care about right or left. Case in point, the strip is being repelled by the peanut, but being attracted to the rod. I don't care if it's attraction or repulsion. What I care about is both are being forced to the right. Therefore, I'm going to add those two together because they're both being forced in the same direction. Here, they're both going to the left, so I'm going to add both of those together. Go in the same direction. Good with that? Do not think, oh, it's attraction, that's positive. Repulsion is negative. Nope. Do not put a negative sign in the math equation for the charge. Like, drop that. You should just have absolute values of the force, and then you're figuring out which way from just your brain. Good with that? Okay, here's something cool. This is like one of those I want to blow your mind conversations. So, to date, that we know of, there are 4 fundamental forces in the universe. Gravity, which we're down with. Electrical force, which we'll talk about, which we are currently talking about. Strong force and weak force. Okay, I'm going to hit strong force and weak force real quick. So, where are protons found? The nucleus, right next to what? Neutrons and other protons. Protons and protons are really close together in the nucleus. what do protons want to do to each other? Repel, but yet they're not. They're really tightly packed. Why? The neutrons. They're like the pacifists. They're like, come on, guys, why can't we all get together? Nope. Neutrons don't do anything but add mass. The electrons are like, stay in there, stay in there, stay in there, stay in there, stay in there. Nope. There is a force that is stronger than the force of repulsion. There is a force of repulsion present, but there's a stronger force we called the strong force that holds those together. Okay? The strong force only happens when you're really small distances, like the size of a nucleus of an atom distance. Okay? And that's the force that holds it together. There's a potential energy associated with that strong force, and that's the energy that is released when you have a nuclear reaction. So we take the atom, the nucleus of the atom, and we break it apart, releasing that potential energy. And that's why you get so much energy out of a nuclear reaction. Okay. There's another force at the subatomic level, and it's called the weak force. It's weaker than the strong force. It's separate to it. So those are four fundamental forces. So I want to consider last semester we had 5 popular forces. We had gravity, applied force, normal force, friction, and tension. The rest of those forces can be boiled down at a microscopic level to be the electrical force. It's how the atoms and the molecules are bound together. So when I touch something, my molecules of my finger are being repelled by the molecules of the stool. Kind of like how 2 magnets, like a North Pole and a North Pole, are brought together and they repel. They don't touch each other, but they're repelling. So when you touch something at a microscopic level, you're actually not touching. It's just being repelled electrically. So like the whole like, I'm not touching you, I'm not touching you, like, I'm not touching you, I'm not touching you. If that's the case, then how are we able to, like, if we're not technically not touching you, how are we able to, like, feel it? Beautiful question. So how do you feel being touched? Like you know, and okay, so at a microscopic level, when you touch something, the molecules in your skin and your finger are being repelled by other molecules, and it pressurizes it, like, and so that triggers your nerve endings, send a signal to your brain like, hey, there's a force of repulsion being pushed on. I'm touching something. So like people are like, well, how do you get stabbed with a knife? Like the molecules of the knife are strong enough to like repel skin molecules, and so it's like they just part ways. They're like crazy, right? Yeah, yeah. And then they like repel the blood vessels, and so they part, and so then that's a hole for blood cells to escape out of there. And crazy, yeah. That's why he believed he gets stabbed. Okay, so that there's one bit of mind blowingness. Here's the other cool thing. I don't know if you noticed, but like the striking similarity between gravity and electric force, like a spitting image of each other. Okay, and these are two of the four fundamental forces of our known universe. They're like a mirror image of each other. Here's another crazy thought. So if you were to change this, let's say it was just to r, not r squared, life as we know it would not exist. Electrons would not be held to our atoms, and it'd just be just a smattering of protons and electrons. And if it was even slightly off, like not squared, but like to the 2.1 power, life would not exist. Chemical bonds would not be able to occur because electrons have been held, too tightly. And it's just, man, I am glad for life's sake that it's like, boom, right there on the money. Because if it wasn't, well, you and me wouldn't be here. Cool with that? And there's some other like crazy cool things necessary for life that like, it's like, whew, man, I'm really glad the universe is the way it is, because if it wasn't, yep. All right, give this question a shot. Have a conversation. Correct answer is so we're doubling one of the charges to cause the force to double. Good with that? Correct answer is bouncing buffaloes. Just that easy. Tell your neighbor. Correct answer is E. Quadruple the distance, that's squared. So it becomes 1/16. Good with that. Last question of the day. Have a conversation. Correct answer is domestic dingoes. Dangerous dingoes. All right. So, popular question comes up is like, what's the deal with capital Q? Some people, instead of liking to write Q1 and Q2, just write to make a distinction. Say capital Q and lowercase q. Same idea. So this is situation 1. Situation 2 is going to look like this. Which that would be 4. That's 2. So you're ending up with half of the force. And situation 3, this becomes 4. That's 4. That cancels out with that. Has the same magnitude as situation 1. Good? All right. Want to tell you how lightning works, because that's just cool. So there's some stuff that we definitely don't know about lightning, but here's kind of what we do. In a thunderstorm, there's a lot of turbulence. Okay, you would not want to fly your plane into a thundercloud. Okay, so there's a lot of wind stuff. As things get mixed and churned in there, molecules have been hit off each other, ripping electrons off. Okay, for reasons that we're not sure why, electrons have a tendency to congregate on the bottom side of the cloud. It's usually, not always, and the positively charged molecules are up at the top. Okay, these electrons are close enough to the ground to cause the electrons in the ground to run away. We're kind of charging the ground by induction here. These electrons in the cloud are not happy campers. They would rather be somewhere else, more positive. And so they send out scouts, search parties to go, hey, let's find better lands. These are known as step leaders. Okay. So you don't see these. This is not lightning. Okay. So they're moving out. As these electron parties or scouting parties go out, they're making the ground more and more positively charged. And so much so that the air molecules near the ground are, so the neutral air molecules are attracted to, let's say, a blade of grass or something like that. And so it's brought in and it takes the electron, this takes the electrons off the air molecule. Electrons hit this and are out. So now you have this positively charged air molecule. Okay, you know how I've preached like positives don't move, they're stuck in the nucleus? Okay, that's true for a solid. But if your molecule is a gas, your proton is still stuck in the nucleus, but the whole nucleus can move because it's a gas. Does that make sense? So you get these gas molecules that are now positively charged start moving upwards. These are called positive streamers. When one of these step leaders connects with one of these positive streamers, that's when the magic happens. Okay. Once these connect, then the electrons right here nearest connection can rush down. Okay. Remember in chemistry, what produces light, like an electron gets excited, it jumps to a higher orbital state, and then when it falls back down, it emits a photon. Yes, no, yes, yeah, no. Okay. So let me just tell you, electron gets excited, jumps to a higher orbital state, and then when it falls back down to its original state, it emits that energy as a photon, as light. Okay, so these Russian electrons excite the electrons in the air around that, so they jump out, and when they fall back down, they emit light, and that is what you see as lightning. Okay, and so it's kind of like, you know how like your cars are lined up at a stoplight, the light turns green. The cars that are nearest the stoplight can go first, and then the cars that are back up here have to wait for all these to go. So as they're going, they're emitting light. And so if you look at a lightning bolt in slow motion, it looks like the light is going from the ground up. But in reality, the substance, the electrons, are going from the cloud down. Okay. The forks, like lightning forks in the sky, are from step leaders that didn't connect. And they're like, hey, we made it. Oh, yeah. And so they're like backtracking. And so that's the forks that you see in lightning. Cool with that? I'm going to show you a video that's going to tell you the exact same thing I just told you. It's just an animated form. So
begins as a small spot inside the cloud 5 miles up. A spurt of electrons rushes outward, travels 100 meters, then stops and pools for a few millionths of a second. Then the stream lurches off in a different direction, pools again and again. Often the stream branches and splits. This is not a lightning bolt yet. It's called a stepped leader, an intensely charged channel leaping and branching down. As it gets close, its electric field begins to exert a pull on the ground.
When that step leader is within 10 or 100 meters of the ground is now aware of there being a big surplus of negative electricity, which has come down on a conductor, certain objects on the Earth respond by launching little streamers up toward the step leader. Weakly luminous plasma filaments, which are trying to connect with what's coming down. If you happen to be standing there, maybe a streamer is going to leave your head and head toward that step leader. A telephone pole might launch a positive streamer. A blade of grass might launch a positive streamer up toward the step leader. It's that special one which makes the connection, which gives rise to the return stroke, and then this catastrophic 10,000 ampere current flows. That closes the switch.
When that connection is made, the electrons drain to Earth in a blinding bolt of light. The part of the channel nearest the ground will drain first, then successively higher parts, and finally the charge from the cloud itself. So the visible lightning bolt moves up from ground to cloud as the massive electric currents flow down.
Okay, go with that. So this is super cool. This is you can see the step leaders. This is slow motion, like high speed photography. Oh, just kidding. So this is a step leader. You don't see this. That's the lightning bolt. Okay. These are the scouts going out, like find better land, and then once it connects, that's lightning. Okay,
How come we don't see that first part?
So it goes really fast. So this is like milliseconds, and it's faint. So like this is like has this large aperture opening without light. Okay, but also notice how the light goes up, and you can also see the force from the backpedaling, like backtracking over that. Cool that. So here's some pictures of positive streamers have been caught on film. Oh, are you kidding me? And here's a lightning strike.
That big apple strike last night.
You got a free quiz on Monday. That is how it's going from like it was up. How it goes up with that.
Woo! There's a phenomenon where sometimes the streamers will actually go above the cloud.
Really?
Yeah. I've watched a couple of like storm chasers like videos on YouTube. There's sometimes like red streaks in the skies. It kind of looks like the streamers.